Well, we're going to start with one of my favorite problems from last year. You know, every semester I'm always like, you know, if I can just get one good problem, something like that they haven't quite seen before. And this was my favorite from last year. So, what is it? Consider the following function. F of xy, it's x squared plus y squared over 4y if x is not 0. And it's 0 if x equals 0. So it's defined for all values x and y. Well, whoops, typo. That should be a y. All right, good. So now it really is defined for all values of x and y. So sketch and label the level curves for f of xy for the values, or if you like, the heights of -1 and 1/2. What does that mean? Well, level curves, that's also what we call the contour lines. And so the heights here are referring to the output. So we can think of our function as being in 3D. So x and y is our location in the plane, and the output, that's our height. So when we're looking for these level curves, what do? Well, we set x squared plus y squared over 4y. This is our function f of xy. And what we do is we set this equal to -1. So that's what we mean. When we're looking for these curves, that's what we're looking for, is set the function equal to a value. So x squared plus y squared over 4y equals -1. Well, that becomes x squared plus y squared is -4y. All right. Now, what's that? Well, someone said circle. Yeah. X squared plus y squared plus 4y. Move it across. And then we say, well, it feels like a circle, because whenever you see x squared and y squared together, that seems circle-like. So let's make it a circle. What do we need to do here? Plus 4. Yeah. So this is complete the square. See, y squared plus 4y, that's not a square. But if you add 4, then lo and behold, this becomes y plus 2 squared. Now, of course, if we add 4, we also have to do it in a way that balances out, so I can add 4 to both sides. So what do we end up with? Well, this becomes x squared plus y plus 2 squared equals 4, or if you like, 2 squared. So when we want to come and draw these level curves here, what do we have? Well, it's a circle. Where's the center? 0, -2. So I'll say here is 0, -2. What's the radius? 2. Now, so this level curve is a circle. But it doesn't include y equals 0, so I'm going to put a little circle there. And I'm going to label this, because you should always label your contour lines. This was the contour line for -1. So that means if I'm anywhere on that circle, I have a value of -1 in the function. Now, notice there were two things. There's also a 1/2. So you repeat the same process. So you say, okay, set your function f of xy, x squared plus y squared over 4y equal to 1/2. So that becomes x squared plus y squared, multiply through, equals 2y. And we run a similar process, x squared plus y squared minus 2y. What do we need to do now? Add 1. So we're going to add 1 to both sides. And if you do the plus 1, this becomes y minus 1 squared. So we end up with x squared plus y minus 1 squared equals 1, which 1 turns out to be 1 squared. All right, so what do we have? A circle, right. Where's our center? 0, 1. So remember, this was at 0, -2. So 0, 1 would be half as far. So there's our center. Radius is 1. So it looks something like that. And we'll label this as a half. And again, I exclude everything where y equals 0. All right, so that's part A. So those are the two level curves. They look like circles, look like we're starting to build a snowman. Now there's part B. And here's the question. Does the limit as xy approach 0, 0 of f of xy, what can we say about it? Does it exist? Does it not exist? If it exists, what is it? If it doesn't exist, well, why doesn't it exist? So, let's use part A. See, there's this interesting thing. When you have multi-part problems, sometimes the second part is connected to the first part. All right, well, how can we connect the two? Notice we have these contour lines, which means that whenever I pick any point here, so if I pick this point right here, and I plug into my function, I'm going to get negative 1. Or if I pick that point, or if I pick that point. So what can I do? Well, what I can do is I can travel towards 0, 0 along this contour line. And if I follow this contour line in towards 0, 0, what will I get? What do I think the function should be? Negative 1, because I'm always negative 1 on that contour line. I could, on the other hand, follow this contour line. Now, if I pick a point on that contour line, what's my value? A half. Doesn't matter which point on the contour line I pick. So if I follow this contour line in, what will I think the value should be? A half. So one way I approach, I get negative 1. A different way I approach, I get a half. What does that tell us about the limit? The limit does not exist. Because approaching along different contour lines gives different values. So we can actually use these contour lines to show the limit doesn't exist. So there we go. Ah, what a fun problem. What a fun problem. So, as we wait for a few minutes for the pen to stop, okay. All right. This actually connects back to one of the things we talked about, which says contour lines shouldn't intersect. And we did it when we talked about surfaces. The contour surfaces shouldn't intersect. Because if you have them intersecting, well, that's trying to say, oh, I have two different values at the same time. And you can't do that. A function can only ever have one value. So the real problem was these two contour lines were trying to intersect at the origin. Now, this is just a little bit of information. It turns out, though, that if you were to draw all the different contour lines, what you'd end up getting is you get circles. And so you get circles down below, or you get circles up above. And it kind of looks, what does it kind of look like? Well, if we were trying to sketch this in 3 dimensions, I would do a terrible job of it. But it looks vaguely like this, where you have circles stacked like that. And down below, stacked roughly like that. And they just happen to be all stacked up and aligned right on that z-axis. So that's what the shape is. So, okay. This actually is, we should point out here that when we're taking these level curves, what's happening is we're going through and we're slicing our function for a fixed value of z. Now, we can use slices of functions to help solve some of our problems. And in particular, we said, there's this thing called the derivative. And we'd really like to be able to take a derivative. And they said, aha, last time we ran into a problem in that when we tried to think of the function as everything changing at the same time, we weren't able to come up with a nice derivative. But here's an idea. Let's not have everything changing at the same time. So let's actually do something a little different. So here, what we're going to do is we're going to work in cross sections. So we're going to slice a function. So we're coming up and slicing up and down. So a cross section says, let's hold one of the inputs constant. So as an example, here I have this surface, and you can see just sort of a sketch of the outline, but it's the surface that's coming down. And now what we'll do is we'll fix a value for x, and we're slicing. And if we fix a value for x, then now what happens is when we slice the surface, we just see a curve. So it's a curve where the y is varying and z depends on y. So now, by taking a slice, I get to see a simple one variable function. Z depends on y. Z is a function of y. What's the good news about that? Well, for one variable functions, we've got a great set of tools. In fact, we're really good at taking derivatives of one variable functions. That's our fort. We know how to handle that. So we can start taking derivatives. And I'm thinking, okay, well that's nice. But how do we take really multivariable derivatives? And the answer is, this is how we do it. So all the things you learn from single variable calculus are what we're going to do. We're just going to take derivatives one variable at a time. So here we go. So in this picture here, what's happening? Well, we're holding x fixed, and we're letting y vary. So we can think of, we have this function, we're going to call it g of y, where g of y is f of x comma y, where x right now is just some parameter that's been fixed. And so we're going to take the derivative, g prime of y, and we do what we always do when we take derivatives. We say, okay, it's the limit as h goes to 0, g of y plus h minus g of y over h. And that becomes the limit as h goes to 0. We know what g of y is. So g of y plus h would be, replace y by y plus h. So f of x of y plus h minus f of x y all over h. And we call that partial f partial y x y. All right. So the partial derivative. Now, why the word partial? Well, in some sense, we're asking, how is the function changing as we change one part? So that's why we call it a partial derivative. How are we changing as we change the part we're calling y? All right. Now you could say, what if I want to do x? And the answer is something similar. So you could hold y fixed, and then what you have is you have a function of x. So we can call it some other function, like a kappa or k. So k of x again. Now y is the part that's fixed. X is the part that varies. So again, you can run through the derivative, and you can conclude, okay, we have partial f partial x of xy, where what's happening is x is the part that's varying. So when we look about these partial derivatives, we're asking, how is the function changing as we change just one part? So we're going to change one part at a time. So what happens as we change what happens to f as we change x, or what happens to f as we change y? So that's our partial derivatives. And you should remember that these are somewhat independent of each other. So whatever happens with respect to x, you could have a very different behavior with respect to y. So here's an example. Again, we've taken a surface. So here's our surface outlined in a bluish tone, and then we've sliced where we either fix x, so we get a curve, or we fix y, we get another curve. And so we have these pictures here, these cross sections. So when we're looking for the cross sections, we can start saying, okay, what's the derivative? Well, here, when we have x is our variable and z depends on x, we can say, all right, we have this curve here, and now I can ask about what's the rate of change. But oftentimes when we think about derivatives, what do we like to think about? Tangent lines. So really what's happening is we're coming in and saying, what's happening in this cross section? Well, you get some derivative. So you can think of a tangent line as sitting here. You'll notice that at this point, And when I say this point, at this point, what's happening to our function? Well, what can we say about the slope of this tangent line?
Right as a vector.
Well, this is just a line, and just we're back in 2 dimensions. So we don't have vectors; we just have slope. What's the slope? Positive or negative? Negative. So it's decreasing. On the other hand, I come here. I think about this tangent line. What's that slope? Positive. So I can have different behaviors for my different variables. So it might be that as I vary x, I'm going up. As I vary y, I'm going down, or vice versa. Now, we might say, but how do we get back to just the function? Well, you can probably guess where we're going. You can think, well, okay, if I have this curve here, this line I can think of translating as a line up here. So I could go back to a line in 3 dimensions. And this line I could translate again as to a line here. Then I say, okay, well, but what if I really wanted to get a nice 3-dimensional thing? What would I do? I wouldn't want lines. What would I want? I'd want a plane. So we're going to eventually go and say, oh, we can put a plane here. And what's happening with the plane is that as we slice in one direction, we're catching that line, and we slice in another direction, we're going to catch that line. So that's going to be coming up soon. I think in our next session, we're going to really get into our tangent planes. So I want to talk about notation, because, of course, it's one of our favorite things to talk about, notation. So before, when we took single variables, we used the d to represent a derivative. And so whenever you see a d involved, that indicates you're taking a derivative that's a function of a single variable. So when you see d, that means my function only depends on one thing. And we're going to be consistent about that. So df dx says, aha, I'm taking a derivative of a function which depends on just the one variable we call x. Now this other symbol, you read it out loud as partial, well, that's used when taking the derivative of a function with 2 or more variables. And so we read it partial f, partial x. Now it's a little bit different. This is not quite the same symbol that you're used to. So if you were to say, how do you write the partial? So you write it something like this. All right? So loop it. So if you were doing your old exercises back from when you were young, you just follow the arrows. You go down and you stop. You don't cross through. Now, if you want, we can compare that to the D. The D, now I have to think about how you put a D. Looks like that. So the D is a different one. So you go down, and then you add the little circle. Of course, people probably say that's not how you write a D. But anyways, so now you know how to write these symbols. Now there is a question about our derivatives, because we used to have this beautiful notation that said, hey, instead of df dx, I could write f prime. All right. Well, wouldn't it be nice to have nice notation like that? So we could say, okay, well, that just says the prime indicates derivative. So it's like, well, I took a derivative, so maybe I can write it as f prime of xy. But now I say, oh, what about here? That's also f prime of xy. And now we're like, what's our problem? Yeah, see, the problem is the prime just indicates take a derivative. If you have a function of one variable, there's no real question about what derivative you took. But when you have a function of many variables, it loses its specificity. So we're like, nope, that's not going to work. That's not going to work. So that's not our notation that we're going to use. So the notation we use now, we have to have something which includes information about what derivative we just took. So here, we're going to indicate the kind. So the way we do it is we change the subscript. So f sub x of x comma y and f sub y of x comma y. So now we're going to change the subscript. So when you see an f sub x, that means we took a derivative with respect to x. And if you see an f sub y, that means we took the derivative with respect to y. All right, good. Now I will say there are other notations that do exist. We won't use them terribly much. One notation you sometimes see with derivatives here is you sometimes see a capital D to stand for derivative. So df of x. So when you're doing with functions of multivariables, you would add some notation. So for example, you could say d sub x of f and d sub y of f. Generally speaking, you just sort of add something to indicate what kind of derivative you took. All right. So now that we've mastered this, our basic rule of thumb. When taking a partial derivative with respect to some variable, treat all the other variables like constants, because we're only letting one thing vary at a time. So if it's not the thing that's currently varying, it's a constant. So that can be very useful for us, because sometimes the stuff that's complicated is not the stuff that's going to be changing. So let's try an example. Find partial f partial x of the following function. F of xy is x squared plus x times arctangent of y plus y to the power of 137 times e to the sine of log of y squared plus 7. All right. Now, emotionally, we might look at this and be like, this looks terrible, because we've got the sine inside of the exponent, and then there's a log inside of the sine, and it's going to take a long time for us to unravel this onion. Or maybe it's not. What's the part that's varying? The x, right? So where are the x's? Well, there's an x squared, and there's an x, and that's it. Notice over here, the really unpleasant part, there's no x's involved. So from the perspective of taking a derivative with respect to x, how do you treat this last part? It's a constant. So with respect to x, this is a constant. Now, of course, if we change the question and ask, what about with respect to y? Then we're like, ugh. But with respect to x, it's a constant. So as far as partial f, partial x goes, well, the derivative of x squared, 2x. Derivative of x times arctangent of y, arctangent of y. Because, again, the arctangent of y, there's no x involved, so it's treated like a constant. So what do we have is we have a constant times x. So when you take the derivative of constant times x, what you get is the constant. And so there's the answer. That wasn't so bad. All right, we won't do partial f, partial y, but maybe we'll do something more exciting. So find g sub x and g sub y, where g of xy is going to be a function that we're going to create. All right, time to make a function. And you can even be a little creative. What would you like to take the derivative of? All right, there was a y, 7, there was an arctangent of x. All right, what else?
E to the sine of e to the 2x.
All right, how about e to the 2x plus y? And let's be, like I said, creative. X to the y. We can do that. We can have x to the y power. We have to restrict our domain. Well, let's just say, okay, we'll assume x is positive, and then there's no problem. All right? Plus pi. There we go. All right. So let's go through. So let's take the derivative first with respect to x. So g sub x. All right. Y to the 7th, how do we think of that? It's a constant. So we have a constant times the derivative of arctangent. Derivative of arctangent, 1 over 1 plus x squared. The derivative of e to the power 2x plus y, what will that be?
2e
Right, 2e to the 2x plus y. What happens is the exponential function, derivative of the exponential function, is the exponential function again. So we're doing a chain rule. So it's e to the power of what's on the original function, 2x plus y, times the derivative of 2x plus y with respect to x. So that's where we get the 2 from. How about x to the y? Y to the x to the y minus 1. What's happening here? Well, here we have the rule of x to a power. And if you say, look, if you have x to a power, you bring the power down. That's the y came down. Then you subtract 1 from the exponent. All right, so that's good. That works. That's correct. What about the derivative of pi? Yeah, it's 0. It's a constant. That really is just a constant. All right. Good. 1 down, 1 to go. G sub y. Well, now we come to the first term. What's going to be the part that changes? The y to the 7th. The arctangent of x is a constant. All right, what's the derivative of y to the 7th? 7y to the 6th. Arctangent of x. How about the derivative of e to the power 2x plus y? So it'll be e to the 2x plus y. And here, when we apply the chain rule, the derivative of 2x plus y with respect to y is 1. So the rules still work the same. We still have product rule, we still have chain rule, we still have all these rules, because we're really doing single variable calculus. We're just having to say which part is the part that's varying and which part isn't. And once you get to understand, it's like, okay, if I'm taking derivative with respect to x, all these y's are constants now, then it becomes great. It's a lot of fun. All right, the derivative of x to the y. Ah, someone knows that off their head. Good. X to the y, ln of x. Now, for those of you who don't remember that, in general you had the following rule. Well, let's just make a couple of observations. We know that the derivative with respect to y of e to any number times y is that number e to that constant times y. So that one people are comfortable with. So how do you get something when it's like in x? Well, now what you do is you add a few more steps. So derivative of x to the y, well, what you do is you say, hey, I really like it when I have e to something times y. So x becomes e to the natural log x, because e and natural log are inverses of each other. If I take e to the natural log of x, you'll get back to x, to the y power. But that's the same as derivative of y of e to the natural log of x times y. So notice, now I'm back here, where I have my constant is this natural log of x. So I end up with natural log of x times e to the natural log of x times y. But now I just undo what I did before. I can go back and say that this part right here is x to the y. So we get x to the y natural log of x. So that's where it's coming from. All right, good. Now, that's if we have functions of 2 variables. What if we had functions of 3 variables? Well, the answer will not surprise you. What you do is you just say, I'm just going to vary one thing at a time. And so you still are doing one, single variable calculus. So, you can imagine you have a function of x, y, and t. So you can think of here as you have things are varying with time. So maybe you have a surface. We think of a surface as being a function just of x and y. But then maybe our surface is moving. So maybe we're trying to model, say, a melting of a glacier. And so as time progresses, the glacier might shrink a little bit, or maybe if it's winter, it might expand a little bit. So the surface moves with time. So we can imagine that both x, y, and t affect the current output. And of course, we don't have to stop at 3. We can have any number. But most of the time, for our purposes, 3 is enough. So let's do one more. All right. h of x, y, t. What do you want to be your function?
X squared, y squared, t squared.
X squared, y squared, t squared. All right. Anything else? This is your chance to channel your inner creativity. Stump the professor. X times y to the t. All right. X to the y to the t. Now, to be clear, do you mean x to the power y to the power t, like that? Okay. All right. All right. You chose this. You chose this life. I didn't choose. Okay. I think that should be enough to confuse me. So, all right. So, how many partial derivatives will we have? 3, right? Because it didn't specify how many there were. How do we know there are 3? There's 3 variables. So partial derivatives ask what happens as we vary one part. Well, there are 3 things we can vary, so there are 3 partial derivatives. So where are we going? Well, we start, it doesn't matter where we start, but we oftentimes go, x, y, t, so h sub x. All right, well, the root of the first part, not a big surprise, 2x, y squared, t squared, x times y to the t. Well, x is the part that varies, y to the t is a constant. We'll end up with y to the t. And x to the power y to the t, well, the y to the t comes down. And then we're going to have x to what power? Y to the t minus 1. Okay, no surprises. Now, let's do our next one. H sub y. The x and the t are constants when I'm doing derivative with respect to y. So we're going to get 2 x squared y t squared. Come to the next term. X is a constant. Then I have y to a power. So that's going to be x. The power comes down. Y to 1 less power. Okay, that's not so bad. Now I have to do a chain rule, because I have y to the t is inside x to a power. So first off, the derivative of x to a power. Well, x to a power will be x to that power times the natural log of x. All right, are we done? No, because the chain rule says now you have to take the derivative of the inside. So we're going to take the derivative of y to the t. Well, we actually just took the derivative of y to the t. That here, since y is our varying part, the derivative of y to the t comes down, y to 1 less power. And now we're done with that part. But the fun continues because we have one more derivative to do. All right, well, our last one, h sub t. First part, well, 2x squared y squared t. Plus, all right, coming to our next term, well, the t only shows up here in the exponent, so it's going to be x, that's the constant, derivative of y to the t, well, that's y to the t times natural log of y. The last part, well, it's a chain rule, because t is inside this y to the t, which itself is inside x to the something. So we start working our way in. So it's x to the y to the t times the natural log of x. And now we take the derivative of y to the t, which will be y to the t times natural log of y. and then we're done. That's not so bad. That's not so bad. All right, good. Now, well, we've taken some partial derivatives, but one of the things we remember is when we took derivatives, we said, hey, why stop at just one? Let's keep going. So we can do what are called higher order partial derivatives, which is derivatives of derivatives. So that's perfectly fine. In fact, that might be a useful thing for us. We saw, for instance, when we talked about things like motion, that if we took a second derivative, we got information, we got acceleration. And also we learned when we took a second derivative, we could learn about what's called concavity. And there was wonderful things like a second derivative test. And so it might be good to have some of these higher order derivatives. Now, the basic idea of a higher order derivative, that's not too surprising. It's just a matter of getting the notation right. So here, if I have a function of two variables, so I'm thinking of f as being a function of x and y. So f of x comma y. Then what I can think of is I can think of there being four different second order partial derivatives. Now the reason I say there are four is because I have to make a choice of which one comes first. So I can take the derivative with respect to x as the first round, and then I can take the derivative with respect to x again in the second round. So that's the derivative with respect to x twice. Now in terms of notation, well, we can write that as the second derivative of x, so partial squared f, partial x squared, so two derivatives of x, or as f sub xx. I could have chosen to first take the derivative with respect to y, and then take the derivative with respect to x. So in our notation, it's either partial squared f, partial x, partial y. You'll notice here that you match partial x, partial y. On the other notation, we write it as f sub y x. So you might wonder what's going on. Well, it's just a matter of how you read things. So when you're reading f sub y x, the first term is the first derivative, the second term is the second derivative. On the other hand, in this notation, you work in the other direction. So you say, first I took derivative with respect to y, and then the derivative with respect to x. So notice here, we took a derivative of each kind. So either y first, then x, but I could have done x first and then y. So it looks very similar. We just sort of reverse things. So f sub xy, or partial squared f, partial y, partial x. And then our final one is, of course, partial squared f, partial y squared, which means we took two derivatives with respect to y. That's f sub yy. Now, you might start to get nervous here and ask the question, are these the same? So in other words, does it matter which order I take derivatives? Now, the answer is these are the same for nice functions. Now, you might wonder, what's a nice function? Well, a nice function is the kind of functions where these are the same. Now, every function that we're going to talk about is a nice function. There are some sort of pathological examples where they don't match, where it does make a difference. But in our class, they'll be the same. So you go ahead and assume that they always match. So in other words, you just need to do one of the two. And we'll check, we'll do an example where we'll do both, and we'll say, aha, they match up, woohoo! So these will always match for our class. So we use nice functions. That's the important thing to remember. Okay. Now you might say, okay, well that's the second order derivative. Can you go higher? And the answer is sure, of course you can. You can go as far as you like. So you can also, for example, take the fifth derivative of partial z squared, partial y, partial z, partial x, okay? Or as you say, f of z, z, y, z, x of x, y, z. Now you might wonder, first off, would you ever do this? And it's like, well, you can do this. And you might wonder, well, why did you choose that specific set of partial derivatives as an example? Well, it turns out that this is a word, zizix. And it's a location in California. If you're ever in Southern California and you feel the need to lose money, so you start driving to Las Vegas, it's the last stop before you hit Primm, which is the first place you can gamble. It's on the border between California and Las Vegas. So there's this place called Zizix. On a side note, there was also a movie that came out that was called Zizix, and it made 20 at the box office. And you're like, wow, 20 million. No, $20. And it did not do very well. So probably because people didn't know how to pronounce it. So, okay. All right. So let's do a quick example. So find all second order partial derivatives of the following function. X squared e to the xy plus y cosine of x. All right. So we're going to find all of them, which means we're going to find 4, because there's 4 different second order partial derivatives. In the future, you can skip 1 and just do 3. But for now, we're going to do all 4. If I want to get to the second order partial derivatives, what should we do first? The first order partial derivatives. In other words, if you want a second derivative, you got to start with the first derivative. So we start with our first derivative. So we're going to use our f sub x. Okay, the derivative of x squared e to the xy. Two x e to the xy. Anything else? Well, plus, be careful here. What rule do we need? Product rule. So derivative of the first times the second plus the first, which is x squared, times the derivative of e to the xy. Derivative of e to the xy? Y e to the xy. All right, derivative of y times cosine x? Minus y sine of x. Because the derivative of cosine is negative sine. The y comes along for the ride. F sub y. Well, derivative of x squared e to the xy. X cubed e to the xy. Derivative of y times cosine x. Cosine of x. Because cosine of x is a constant. All right. First derivatives out of the way. Ready for second derivatives to begin. So we'll start by taking the derivatives of f sub x. So we get 2 of them. First off, f sub x. Well, in the interest of time, product rule again. So that'll be 2, derivative of 2x, e to the xy, plus, and now the 2x, and then the derivative of e to the xy will be a y e to the xy, plus, now come here, we'll need another product rule, x squared times e to the xy. Well, so derivative of the first, that's the x squared part, so that'll be 2x, y e to the xy. And then plus, taking derivative here, x squared, because we're product rule, then we have y, and the derivative of e to the xy, well, that's another y e to the xy, so we get a y squared. And then the derivative of y sine x will be y cosine x. Okay, so there's our f sub x. Now, if we wanted to, we could say, hey, these 2 terms in the middle combine. That's not a coincidence. They actually would combine in this case. We wouldn't have to unless we were told explicitly to simplify. And so here we will not. All right, because we want our space. F sub x, y. So this says first take derivative with respect to x, and now we're taking derivative with respect to y. So we're coming up to the f sub x. That's what we're cluing off of. So here, the derivative of 2x e to the xy, well, there's only a single y, so we're going to get 2x, and the derivative of e to the xy, well, it's e to the xy times the derivative of xy, which is going to give us another x, so we get 2x squared, e to the xy. Then we come over to this term, and we get, okay, well, here, when I'm taking the derivative with respect to y, I have to do a product rule. So I'll get the derivative of x squared, well, that's a constant. The derivative of y is 1, so we get x squared times 1, which is x squared e to the xy, and then plus x squared times y times the derivative of e to the xy with respect to y. Well, that would be e to the xy times an x. So that's going to come down, x squared times x gives x cubed. Then the last term, derivative of minus y sine x with respect to y, well, that's going to be minus sine of x, because the sine of x is a constant. Now we're going to compare that to f sub y x. So that says take the derivative first with respect to y, then take the derivative with respect to x. So we're coming up now, we're looking at f sub y. So taking the derivative of f sub y with respect to x. So x is our variable. We need to take the product rule. So the derivative of x cubed is 3x squared e to the xy, derivative of the first times the second, plus x cubed times the derivative of e to the xy. Well, that's y e to the xy. And then the derivative of cosine x, that's negative sine of x. Okay, the last one, f sub y. Well, now we're taking the derivative of f sub y, so we come up here, take that with respect to y. So the x cubed is a constant, derivative of e to the xy would be e to the xy, but then we bring down another x, so we're going to end up with x to the fourth. Derivative of cosine of x goes away. Now, maybe we'll be a little bit nervous because we said just a few moments ago that f sub xy and f sub yx are supposed to be the same. But are they? Now these parts match on the end. Does this match? Yes, it does match. Turns out 2 plus 1 does equal 3, as we've seen previously in our class. So the process of getting to the answer might vary, but the answers will be the same once you simplify. One more idea. There's something called partial differential equations. So partial differential equations, the word partial comes from the idea of partial derivatives. Now these are the kind of differential equations that people care about. So physicists, they care about partial differential equations because they like to look at many things varying at the same time. So there are things called, for example, the Laplace equation. And that says, suppose I have u as a function of xy, so we can get u sub xx. So I can ask what's the second derivative with respect to x, and I can look at u sub yy. The Laplace equation says that turns out to be 0. There's something called the heat equation, where now I have x, y, and time. And that says u sub t is some multiple of this Laplace equation, u sub xx plus u sub yy, and many, many more. So these types of equations, these partial differential equations, they are the foundation of a lot of the things that happen in physics, in engineering, and all sorts of things. Now, the thing is that solving partial differential equations is hard. We have multiple courses on how to solve partial differential equations, and at the end of it you learn we still don't know how to do most of them. But verifying solutions are easy. So what you do, the answer is you plug in and you just say, does it work out? And if the answer is yeah, it works out, then you verify. So we don't learn how to solve them, but verifying, we already know. So an example. Verify that the following function, u, which depends on x of t, which is sine of x plus sine of t, is a solution to the following differential equation. U sub t times u sub xx equals u sub x times u sub tx. I really should say a partial differential equation. And whenever you hear the word partial differential equation, you should always think an equation involving partial derivatives, which is what we have here. So we see we're going to have to take some derivatives. So there's some first order derivatives, u sub t and u sub x. There's some second order partial derivatives, u sub xx and u sub tx. So we should always start with the first order, u sub x. Well, sine of x plus sine t. So cosine, derivative of sine, leave the inside alone, times by the derivative of the inside. Well, because we're taking derivative with respect to x, derivative of x plus sine t is 1. And we're done. Okay, that's good. Now, let's also compute, leave some space here, u sub t. What is that? Well, u sub t, chain rule again, cosine of x plus sine t, because we leave the inside alone, times the derivative of x plus sine t with respect to t. X is a constant, and the derivative of sine is positive cosine. So now we've done our u sub t and our u sub x. Good, good. So what's next? Well, let's do some other terms. Second order. So let's do our u sub tx. What is that? Well, let's put it over here. U sub tx. So we're going to say here, notice that we took the derivative with respect to t. Now we're taking it with respect to x. Because we could also do it in reverse order. In other words, u sub x with respect to t. We'll take a quick look at that in a second. But now, coming down here, the derivative of this with respect to x. Well, cosine t is a constant. So the only place where x shows up, one place. So, derivative of cosine, negative sine, x plus sine of t. The derivative of x plus sine t is 1, plus, of course, we have this cosine of t here on the end. All right, and you can check. So what if I had come here and taken u sub x, take derivative with respect to t? Well, we would have got negative sine of x plus sine t. And then we have to multiply by the derivative of x plus sine t, which is cosine t. So u sub t, x, u sub x t, they're the same. Well, what about u sub x, x? Guess I'll put that here. So it's coming up here. Well, there's only one x, derivative of cosine, negative sine of, leave the inside alone, x plus sine t, and then times it by the derivative of the inside, which is 1. There we go. All right. So now let's see what we have. U sub t times u sub x, x. So u sub t, so there's a cosine x plus sine t, there's a cosine t, and there's a negative sine of x plus sine t. On the other hand, u sub x, u sub tx, well, there's a cosine of x plus sine t. There's our u sub x. U sub tx is negative sine x plus sine t times cosine of t. And now we compare. We say, okay, do they match? Well, they both have a negative. That's good. They both have cosine t. They both have sine of x plus sine t. And they both have cosine of x plus sine t, which means they're the same. And therefore, we have verified it. Because we see that u sub t, u sub x, x, and u sub x, u sub t, x are equal. And that's verifying differential equations. And of course, the fun part, solving them, well, that we save for another class. We can't have all the fun. We got to spread it around. All right. See you next time.